Okay, we come now to a point, or I feel I'm now at a point where it could seem that we become redundant. Yeah, so many, and I mentioned that the expertise of each of the contributors goes beyond its very special focus. You have already now heard that some of the issues became repeated, and this will be also here the case. I hope it is not just a repetition for you, it's also some kind of complementary, because everybody puts some light on the issue from a different point of view. And you already heard about these topics before, and I would like to add some more comments on this from some other point of view. Christoph started today already with the sentence 61850 is much more than a protocol. I think this has to be mentioned again and again, because once a guy told to me, 61850, that's the new protocol for the optical CTs and PTs. Yeah? So this is a perception that we have. You heard it's what there is much more in it. I want to go after these three most prominent protocols: the client-server protocol, GOOSE, and Sampled Values. And to be honest, there is much more which can be called a protocol. We have this 61850-90-5 part, which covers that what is called by Alex the routable GOOSE. So to bring this information over wide area communication networks. We will hear about the redundancy protocols which have been included in the 61850 scope. Then time synchronization now has also with -9-3 a 61850 number. We will hear about that tomorrow in a different presentation. And there is also something going on with mapping on web services, something that we had to exclude from this event. It would just become too much. Yeah, and even here, I will only go over a smaller scope. And also, Christoph showed you something like that. The question is, where do we have 61850? And let's first start on what we had before as protocols, so to say, in place. We had very well defined interfaces here at the process level with the secondary quantities that we used. There were some variations in the nominal voltage and two major nominal current values, but this was pretty well defined and very well interoperable. We had, for the binary status exchange, we had hardwired interfaces to the switchgear, for instance, and we also had hardwired binary IOs between the field devices on the same level. So literally for every bit of information we had a wire loop there. Then up to the station controller, we already had some serial protocols in place, like the 101, 103, DNP, and whatever. Typically master-slave protocols with multiplexers, slow, complicated. And up to the network control center, we had some other versions of these protocols. Now, I did not mention here 104, but going over DATEX P or X21 or whatever, 64-bit, kilobit serial lines up to the control center. Now, where does 61850 come into the place? In the beginning, as already mentioned by Christoph, it was in the station focus. And here we got now some new ways of interconnecting things. And to get in the data from the CTs and PTs, or let's say the current sensors and voltage sensors, we have now the sampled values in place here. The binary exchange to the process closed devices can be done with GOOSE now, if you have intelligent controllers on your switchgear, and, which is already very well established, the peer-to-peer communication on the bay level between the IEDs via GOOSE messaging. And up to the station controller, we have this client-server protocol now available. Up there, there is more or less mainly the same structure in place that we had before, but as Christoph has also indicated, IEC 61850 is leaving the substation. The scope will be extended and will go upwards as well. Another picture that says more or less something similar is the client-server protocol that we have here for SCADA purposes is something that I would call not time critical. What does mean not time critical? We don't care about 10 or 50 milliseconds or 100 milliseconds. Yeah, it's good that we have an adequate response for the operators in the control centers. And here we have a communication which uses commands which are then also confirmed. And on the other side, we have these real-time protocols. This is time critical. You heard about the multicast mechanism, which is behind that. Because this is very performant, we're using this. And there we have on the one hand the GOOSE protocol between the field devices and the sampled values as the data for the data from CTs and PTs. And here is a drawing which also is in similar form, not as colorful as here in this 90-4 communication networking guideline. And it should show you the following. That you cannot just simply say, okay, here we have something that we call the process bus and there are only sampled values. Or we have here something which is the station bus and we have only client server there. Yeah. Potentially, even if you have segregated networks and you see here, for instance, that here are some routers to segregate a little bit the traffic between these process bus segments, potentially you have all kinds of traffic everywhere. Yeah? For instance, this station controller would like to control this circuit breaker down here, then the client-server communication would have to go through the whole network topology. Yeah? And you just have GOOSE messages on the station bus as well. Also, Christoph talked about this abstract communication mapping and the specific mapping. I come back on this topic because it has a little bit about an effect how people call these protocols. I want to clarify the naming a little bit. Nobody talks about part 7.2 when he talks about GOOSE or sampled values or client server, but in fact, the communication itself, how it should work, is defined in part 7.2. And then we have here the specific mappings. In part 8.1, we have covered two things. It's the client-server protocol and it's the GOOSE protocol. You might ask, why two mappings in one part? This has historical and social reasons. Yeah, technically you could say we should have put that in two different parts, would have made it sometimes maybe a little bit easier to understand. And we have a dedicated part 9 here, part 9.2, which defines how sampled value services are done on Ethernet networks. Same story drawn in a different way, and you have seen something like that before as well. Here we have client server and GOOSE. Defined the mapping in 8.1. The client server going through the MMS protocol and the TCP/IP stack. And you see here the MMS is just a transport protocol for our client-server services. Yeah? And this is why I do not talk about MMS. So when I order a taxi, I order a taxi. I don't say it has to be a Volkswagen taxi or it has to be a Mercedes taxi, because this here is only the Volkswagen and the Mercedes. I want to have a taxi. Yeah. And the GOOSE is directly mapped on Ethernet and the sampled values just as well. And you will see that they are rather similar. Sampled values, mapping defined in line 2. This is how it is drawn in part 7.1. One of the drawings there showing the same thing here for sampled values and here for the client-server protocol. Even in more detail, all the OSI layers drawn out here. Now this SCADA protocol, client-server communication, is unicast. So we have this explicit IP addressing, and this has some effect. Since I'm doing testing, I have to mention that, and it will also be mentioned later. Sniffing of traffic between two participants in a unicast communication is a little bit tricky, because you have to get into the path, and if you want to make testing with that, you're either the client or the server by yourself, or you can somehow tap into this communication. It is a confirmed communication. So you always have something like a request from the client to the server, and the server will bring back some kind of a response. And of course, this takes a little bit longer than what we have in place for the real-time protocols. But the timing, of course, needs to be adequate for the SCADA purposes, so the performance of servers is an issue, of course, as well, and it can be tested. There is a concept in this client-server protocol which is called the reports. When you consider an older protocol like the 103 protocol, the master always had to poll the device. Do you have something new for me? Then it started multiplexing, polling the other devices, and the ID had to wait until the master came back on him and said, do you have something for me? And then the client could, or the server, or slave in this case, could say, yes, I have something. And then the master asked, yeah, give it to me. And it was working like that, and it was rather complicated, and only if the master was really asking. Here we have something different. We have this called unsolicited reports, spontaneous reports. When there is such a client-server communication set up, the client can subscribe to a report, and whenever there is a so-called trigger condition met, which is typically a data change, then the server will send this report to the control center. Of course, there are also general requests, general interrogations, or periodical reports that you can set up. But typically, this unsolicited report is used to get the information up to the control center. Here, this is drawn in a different way. So you have this atomic operations like a read request, where the server will get you back some data, values of data attribute. You can issue a write command, where you say to the server, I want to write a specific attribute with a value. Then you get at least back an acknowledgement. The server will tell you, yes, I've done that, or I refuse that. And then it can become more complex. You can have complex control sequences. We have already heard about this select before operate. There are many read and write operations involved. First to read the control model, then to write the command value, and then the confirmations to that make up this kind of communication. And of course, the reports which can be sent from the server to the client. And as I said, many people don't even use the term client server. Yeah, they just call it the MMS. Yeah, but as I said, it's just a transport protocol. In principle, we could come up with another specific mapping, not using MMS, and we would still have client-server communication. By the way, these web services are exactly doing that. Yeah. Some people also call it 8.1, yeah, and think it's power talking, yeah, but it's even less exact, yeah, because 8.1 also includes GOOSE, so you really can't specify this kind of communication with the term 8.1. Yeah? So I would recommend to use this generic name, client server. Now we go to these real-time communication services. You have heard about that it's multicast. Here you see a snippet from the 61850 standard with the proposed recommended multicast addressing ranges. You see we have about exactly 512 addresses always specified or recommended, and it is possible to group GOOSEs and sampled value streams, so not every GOOSE needs to have a distinct multicast MAC address. By the way, this one here, this is the multicast bit. As soon as this bit is set, the packet is a multicast packet. So it makes sense to think about that, to put GOOSEs into the same multicast address group. So if you want to do multicast address filtering, this is very much beneficial later on. Now let's start with the GOOSE. So the full name is the Generic Object-Oriented Substation Event, a name that was created already back in the past millennium, yeah, for the UCA GOOSE.
97.
In 97, as Alex said. And since this term was so well loved by the 61850 guys, they have just taken over this term from the old UCA GOOSE, and the old UCA GOOSE was renamed to GSSE. But this is history. Nobody uses GSSE in a new system anymore. The main thing here is it has an event-driven timing. When something happens, when we have a data change that needs to be communicated to the other devices, the GOOSE mechanism kicks in and immediately publishes that information. In addition, we have a repetition strategy. We repeat that information because it is an unconfirmed communication. And just to care for the nowadays very unlikely case that a packet is lost, the packets are repeated. And we will see that later on. Here a little bit about the GOOSE structure. A GOOSE has a header and it has a payload. Yeah? And part of the header is, let's say, out there in the Ethernet frame. Yeah? For instance, this multicast MAC address. But even in the uncoded part of the message, we have something, for instance, like the simulation flag. We will hear later on how this is used for testing. We have something in there like an application ID. This is more or less plainly put in the Ethernet frame and can be read out very efficient. And then we have a part which is ASN1 coded, and also part of the header information is in this ASN coded part, and unfortunately this makes it a little bit less efficient, but here we have the unique identifier for the GOOSE. This is the GOOSE control block reference. This is the only identifier which really has to be unique. There are some others, like this application ID, the GOOSE ID or so, but they are not necessarily unique. Yeah? So the one thing you have to really go after is this GOOSE control block reference. But there in the header, we also have status numbers, sequence numbers, telling us about the sequence or stream of GOOSE messages where we can learn, is it complete or isn't it complete? Yeah? And in the payload, we have the data set that contains the data attributes that we want to communicate. And in principle, there could be any attribute of any data type in 61850. Today, we mainly have Boolean or binary information there, but the GOOSE is absolutely not restricted to that. Yeah, we could also transfer a measured value. Some people use the name analog GOOSE for that, when there is this kind of information conveyed. Here we have this repetition strategy. We have a repetition of the GOOSE even if nothing is going on. So at some point we are at the so-called maximum interval, and this is a wire break supervision, yeah? Because this GOOSE message tells us how long it is valid, and within that time you should receive another GOOSE packet. So a subscriber can determine if the GOOSE publisher is still active. But if there is a new event, a data change, the mechanism will not wait until this maximum interval is expired. It will immediately start to publish the new information and repeat it more quickly, just in case there would be a packet loss. And then this timing is extended until we come back to the maximum repetition. Okay, I have to speed up a little bit. This is a picture from the first IEC 61850 GOOSE implementation. It's now 15 years back at the famous Vancouver demo. And you can see on this picture, what can you see in the first place? You see how bad digital cameras were 15 years ago. You see here a Siemens relay, an ABB relay. You see here some switches. You see here a notebook computer, which was for simulating a circuit breaker. And guess who has written this simulation? It has been Jörg Reuter. Yeah. And so, you know, where the usual suspects have been before. Okay, and of course, the GOOSE is a very, very entertaining thing. And if the GOOSE has nothing special to do, it even has its own bar somewhere in Florida. Okay, the sampled value concept, very quickly. We heard that the primary values go through the sensors. It can be of any kind of sensors, doesn't need to be optical. Yeah, it can be a Rogowski coil, it can be a conventional CT or PT or 100 trained hamsters or whatever you can imagine. The information is digitized, and then the sampled value stream goes into the substation network and can distribute it to any subscriber, in this case, to any protection relay that has to do something with that information. We also have a few different names, sampled analog values, sampled measured values. You find that in the documents. Bottom line, we have the sampled values. The timing is now not event-driven, it's periodic. We have regular sampling intervals and regular publishing intervals. As already has been mentioned, Reinhard has said, you have probably to make a very, very thorough investigation of your architecture and maybe filter the network load when you deal with sampled values, because it causes a high stress on the network. You have many megabits per second coming out of a merging unit. And it's again, unconfirmed communication, very fast and efficient. To reduce the variability in the original standard, there has been an implementation guideline set up. It's called 92LE, but this is only a nickname. Yeah? Many people use this term IEC 61850-9-2LE. Yeah? There is no document like this. Yeah? It's just this implementation guideline here that limits the variability, and helped very much in the interoperability. So we have here this 4 currents and 4 voltages in the data set with the defined scaling. Everybody has to use the same scaling. We have only a couple of sampling rates, and here are some figures how the network load would be. Again, here very similar to the GOOSE. We have a header, and also part of the header is ASN1 coded, and here the sampled value ID is the unique identifier that you really can go after. And we have a payload. Typically, we have only numerical values in float or integer format to convey the voltages and current values. And in 92LE, as was stated on the slide before, it's only integer values. A little bit about the timing. Here is an example how that would work with 4000 Hertz, with one version out of 92LE. Here are the points in time. This is the start of the second, the top of the second, and that's the time after the start of the second, where we sample values with this sample count here. And then in the merging unit, we have some delay, and here it would be 125 microseconds estimated, when the packets are then, after the conversion, sent out on the network. And you see I have drawn this already unevenly spaced, because there could be already some jitter in the conversion when the packets come on the network, and then they go through the network. And then the packets are even further delayed until they reach the publisher. And you see, by purpose, I have put here some random timing in. You can even collect more jitter on the way through the network. But this is not really a problem, because the specification just says I need to get it within 3 milliseconds after this point in time where I have taken the measurements, and the subscriber has to deal with this delay and this jitter.
1 minute.
Thank you. This is something special. This is a complete protection test. Do you see something that hits your eye on this complete protection test? Okay, to make it short, I only have 30 seconds. There is nothing connected here to the banana plugs. Yeah? This was the first fully sampled values and GOOSE protection test, and it was in September 2005. Yeah, it's more than 10 years ago. I can't understand why this is not in every substation today. And there is a new standard coming up for sampled values, extending the concept of 92LE, putting some very nice things in place. You see here, it takes over 92LE as a normative part, yeah, but it added 2 new, very interesting variants, which go with the same packet frequency. So we have, when we mix these variants on the network, all packets with the same frequency, what can be very nice, and we just do sample packing to get to the sampling frequencies that we need for the application. And there is some obscure, crazy version that I hope will never become effective. Okay, that was it for this part. Thank you very much.